Hello everyone, I'm José Correia and I'm going to present some work I've developed with collaborators both at the University of Helsinki and the University of Basque Country in Bilbao. So this is based on a recent paper called The Spectrum of Axions from a Scaling String Network, and I think the best place to start is to just introduce the axion itself. So the axion arises as a particularly promising dark matter candidate, and it arises after a solution to the strong CP problem. Now, I say that it's a promising dark matter candidate mostly because it can be abundantly produced in the early universe. So, depending if these are produced pre or post inflation, generically, its call is simple enough to produce them. They are produced with very low kinetic energy, so they are going to be light and inherently cold. And they are weakly interacting and stable. Now, there are multiple experiments searching for these. And of course, there's quite a large range of frequencies and masses that one has to probe. But especially in the case which one is considering, say, for example, the search of axions in the post-inflation range, it would be important to have better mass estimates to provide these experiments with, say, a specific range to look for. Now, how do axions appear? So every single time there is sort of this PQ mechanism. In general, there's always some sort of complex scalar field, which is invariant under some U1 global symmetry. And there's going to be some phase transition at which this global symmetry breaks. And if this global symmetry breaks post-inflation, then we will have these sort of one-dimensional objects called cosmic strings appearing. And the way they appear, or the easiest way to think about their appearance, is to basically imagine this sort of Mexican hat type potential. Imagine, say, regions or sort of Hubble patches corresponding to a specific choice along that sort of minima. And essentially what one is going to end up is that there's going to be some regions which are indicated by sort of the white dot, which are basically trapped at the high symmetry phase, basically, so at the top of the potential. And around it, you just end up with this sort of continuous change of phase. By the way, excitations, angular excitations are basically axions in this case. Now, if I take a look at all of these sort of trapped regions and I try to connect all of them, I end up with something called a cosmic string, right? So now, we don't usually just form a single string, in particular because, again, all these correlated choices happen on scales of a Hubble patch at most. So what we end up forming is a network of strings. And in case of a network of axion strings, these are just going to emit axion waves continuously for at least 70 e-folds after forming in post-inflation until the QCD phase transition. And then at this point, essentially, there's a second symmetry breaking, which will dictate that we end up with a sort of tangle of strings and domain walls. So it looks kind of like soap. Now, in this talk, we will only address strings, and we will try to use simulations to try and think about these. Now, the problematic part about simulations overall is that they do not necessarily have the necessary dynamic range for us to simulate, say, starting from inflation all the way to the QCD phase transition. So, of course, a lot of the predictions that one can make about the amount of axions produced and the corresponding mass are obviously limited by extrapolations that one makes. So in some sense, it's not entirely surprising that, for example, for the post-inflationary scenario, we end up with a rather active research area. So the dark matter mass prediction can be affected by many factors, and depending on how one chooses or how one interprets the simulation's results, it's possible to obtain very different answers. Now, although many factors impact this, I think I wanted to just highlight two. So for simulations which assume field theory, so let's put, like, say, a complex scalar field discretized in a co-moving grid. Two factors that I can think of is, for example, the number of strings per Hubble volume at the phase transition. If this thing is, for example, constant and goes to order 1, or if, for example, it has been continuously growing as a logarithm of time throughout 70 orders of magnitude, so essentially it ends up with most strings, or the emission of low momentum axions. So depending if the power spectra is scale invariant or peaked at the horizon, we will end up with a different abundance of axions. So usually we end up with more axions when it's peaked at the horizon. So I didn't say, but essentially when one assumes that the number of strings per volume is constant, what one is assuming is the notion of standard scaling. So defect networks are usually expected to evolve towards a so-called scale invariant regime or scaling in the radiation epoch. And that essentially means that the mean string separation is going to be proportional to time, and that the string velocity is going to be constant. And therefore, if I look at a specific network at time t1 and at time t2, I will not be able to statistically distinguish between them. I will see the same number of strings, or strings with the same properties as well, so with the same separation, with the same velocity. Now, scaling usually is expected to occur if sufficient time has passed since the time of formation, and also if the mean string separation is much larger than the radius of the string. Analytically, one can also show that this corresponds, so via network and semi-analytical network modeling, that scaling also corresponds to a fixed point attractor. And this usually kind of results on having a mean string separation, which is roughly proportional to the horizon. Now, scaling is interesting in the sense that it occurs due to energy loss. So it's actually sustained via energy loss mechanisms, such as, for example, the formation of smaller loops by strings, the emission of radiation, or even the expansion of the universe. Now, for today's work, I was going to basically show simulations which occur in teracyte co-moving fixed grids. They were performed at LUMI, so it's the 9th most powerful supercomputer in the world as of right now. And as I'm saying, the idea is to take just the simplest possible axion that one can think, so just a complex scalar field and its conjugate on a grid. So think of this as a discretized version of the equation of motion we see there. And then we want to study the evolution of the network, and we want to study the emission of axions. Now, in order to be successful in this, there's one thing that is important, which is to obtain as much statistics from either low density or high density networks, especially because we want to understand how the network evolves towards what attractor, if it is, which one it is, for example, and then also to try and control which effects happen in the axion power spectra themselves. So note that we always assume that they will be driven towards some sort of evolution attractor, but if there is no agreement on this attractor, it is of course important to probe as much of the phase space. Now, that implies that for our initial conditions, we will start with a Gaussian random field. This Gaussian random field will have fluctuations which go either at 5 lattice sites or at least 320, for example, and we will be using the largest 16,384 cubed runs in order to study the evolution of the network, and the 12K runs, which are the meat and bones of this presentation, at 12K, basically. This is because they use power spectra, so they're more memory intensive. Now, the 16K runs were important for a previous publication, where we actually tried to study the evolution of the network and to assume that and to show that in principle there is going to be this evolution towards a constant number of strings per Hubble. So allow me to just present a very brief overview, and also just to pinpoint exactly why studying as many initial conditions as possible is important. You can see that, for example, for the higher density initial conditions, so for example 5, 10, or 20, the rest frame string density actually converges to a constant, which is indeed consistent with the notion of scaling. On the other hand, the string velocity is still showing some evolution. On the other hand, for low density initial conditions like 320 or even 160, it's quite obvious that the velocity does indeed converge to a constant, but however, the rest frame string density does not. So what this implies is that in reality there is a phase space, or there's an evolution phase space, which not only is telling us that there is a fixed point, but in principle there's going to be two null climbs. So one which is consistent with less evolution in the velocity, and one which is consistent with less evolution in the rest frame. Notice that most groups that presume that the number of strings increases over time usually use the universe or measure the universe frame string density. And I have more details about the differences on how to measure these two in backup slides. But the important thing to notice here is that in our work, the universe frame string density has not converged. But if we apply the boost factor, for example, derived from the string velocity, we do obtain convergence, and we do get it to coincide. Note that the rest frame string density is the one that's related to, say, energy density, and therefore to the mean string separation we have, say, predicted from a semi-analytical model, for example. Now, for the axion energy spectrum at sub-horizon scales, or essentially between the horizon and the string width, there are basically two possibilities. In one of these, one ends up with a background of loops that is collapsing as fast as possible, and therefore the actual spectrum is basically going to be scale invariant. So that's given by the Q=1 hypothesis, where essentially one ends up with a population of loops which take multiple oscillations to fully disappear, to fully decay into axions. And in that specific event, the spectrum itself is going to be larger, with Q larger than 1, and essentially it's going to be peaked at the horizon. So it's going to be peaked at the curvature radius of the strings. Now, it goes without saying that this is not a simple exercise, and it's plagued by a lot of systematics, and I would say by probably the largest systematic of them all, which is the interpretation of one's results. And therefore, it's no surprise that groups have had different interpretations, or at least different conclusions. I would say that probably the most important thing to take in mind is that so far, at least until now, until recently, there has been no model for the actual power spectra for the whole network, right? So for an ensemble of strings. And to keep again this idea of ensemble of strings, I'm just going to point out to the audience that field theory simulations of single loops have so far been consistent with rapidly decaying loops, so Q=1, and those of locked strings have been consistent with Q larger than 1. Now, before we move on, I think it's important to call attention to a specific systematic, which is called a self-field. So global strings are not completely confined to a tube, with their energy density also having some contribution, say, in other scales beyond, say, the actual width of the string, which implies that when we're trying to look at the axion energy spectrum, so of axions emitted by the strings, it's quite possible to also have some non-propagating modes from the strings themselves. So what this means is that when I try to define my observables, I should do as much as possible to ensure that these are as clean as possible. In this particular case, and given that we're looking at the angular part of a complex scalar field, we're going to define two currents. So one temporal current, which is the one that's used by most groups, and a spatial current, which in principle should be less polluted, as Drew and Battier et al. Have also pointed out. Now, in these last two references, they actually went a bit farther. So it wasn't just using the spatial part of the current, but there was also the idea of using real space radial projections of the currents. In our case, what we're going to do is we're going to do projected observables, yes, but we're going to do the projection in Fourier space, which is much easier to do for networks. The two projected quantities we're going to get, one is longitudinal, so that's J of S, which would in principle contain axions with some proportion of self-field, and the J plus and minus, which are basically the transverse projections, and these are only for strings. Already from here and from the power spectra of these quantities, I can see that, for example, the difference between P of 0 and P of S are of similar magnitude to the string energy part, and also have a similar shape at subhorizon scales. What that implies is that, in principle, these are both reasonable or sensible estimates for a self-field contribution. Moreover, and when it comes to defining or to actually getting a model for the power spectra, again, let's just take this picture of an ensemble of strings, and let's take also a page out of CMB power spectra. And we're going to introduce a modeling framework which is called the unconnected segment model. Here, power spectra are constructed from the spectra of individual n string segments with random orientations, average velocity v, and length L. And L can be given by the mean string separation here. Now, the model is going to be crude and obviously with some caveats, because essentially I only have straight string segments, but essentially it already gives a couple of predictions. For example, it already tells us that the self-field contribution to J0 is going to be of order v to the squared, and the contribution to J of S, so the projected spatial part of the current, is v to the fourth. So this tells us that in principle J of S should be cleaner than J of 0. The model itself also predicts that the maximal value of Q should be 1 for subhorizon scales, and therefore one should have at most scale invariant spectra, and gives us some useful things like the ratio between magnitudes J plus and minus J0 and S. The time decorrelation of observables is also predicted. Again, before we compare it to the simulations, I will caveat again that this is a crude model, and I will also refer the audience to the model of Battier et al., which, despite being different, is also in the same spirit of finding a power spectra from an ensemble of strings. Now, comparing to what we actually obtain in the simulations themselves, we see that the spectrum of axions is roughly well described by the unconnected segment model prediction. So again, we just have this sort of logarithmic spectra consistent with scale invariant power spectra. We see also that for simulations which do not have, for example, the lowest possible initial density and stay close or sufficiently close to the asymptotic values or the asymptotic predictions for a scaling network, that this also collapses to a single curve. So that's a self-similar power spectra. The ratios between the spectra are also estimated reasonably well by the unconnected segment model. In addition, we can try to study the rate of change of the power spectra themselves, which is a variable that's used by network groups so far, but which unfortunately I would say is extremely noisy and affected by multiple systematics. We can say that we are roughly consistent with Q approximately 1, and we can say also that there is some very minute time growth associated here. I would probably put the interpretation of this growth as being related to just an increase of zeta w, so the universe frame string density. But again, we know that this should cease because of the existence of standard scaling. In conjunction with the unconnected segment model, we also get the scale invariant Q around 1 answer. There is a presence of a subspike, which is denoted here by the vertical line on the lower right figure, which we interpret to be a resonant axion production. Instead of studying these variables, we can also move on to another spectra, which is the co-moving axion number density spectra, which essentially, and again for initial conditions which are denser, such as alpha equals to 20, also reveals the sort of self-similar collapsing spectra to a single curve. This also signals that in principle the evolution of Q should cease at some point. Notice that the lower initial density, initial conditions, so such as alpha equals to 80, generically yield towards the end of the simulation power spectra which have not yet converged. And I would like to point out to the audience that this is consistent with groups, this is essentially the preferred initial conditions of groups which prefer the scaling violation, or in our interpretation, an approach to scaling. A dimensionless number density also allows us to study how the self-field contribution affects the number density itself, and it tells us that there is an overdensiment of roughly 30% if one tries to use the time-like current. Based on the spatial current, we can also see that there's evolution towards a constant value approaching from above or below, depending on the initial density. And this is also another telltale sign of scaling. Given that the string walls contribution is important, we leave the full mass prediction for the next publication. So to conclude, we have reviewed previous work which provides further evidence that axion strings exhibit standard scaling in lieu of a scaling violation, which we interpret as an approach to scaling. In our newest publication, we have proposed a model to try and predict what the power spectra produced by an ensemble of string segments should be. And this model is quite useful in terms of giving reasonable shape agreement for the actual spectra that we're trying to measure in the simulations. We have also proposed new observables, and we studied self-field contamination. We can claim that we have seen self-similar scale invariant axion power spectra emerge. The self-similarity itself is a clear sign of standard scaling. The fact that we don't necessarily favor the time-like current, as it is a more polluted variable, implies that we get a cleaner and lower number density overall than groups which have used this polluted variable. The number density as well, estimated with the spatial current, also reveals convergence to a constant number axion number density, which is consistent with standard scaling in the Q=1 picture. The full mass estimate with the collapse of string wall networks is next. Thank you.